Reaction mechanism and reaction coordinates from the viewpoint of energy flow. Wenjin Lee and Ao Ma, Department of Bioengineering, the University of Illinois at Chicago, 851 South Morgan Street, Chicago, Illinois 60607, USA. Received January 18, 2016. Accepted February 26, 2016. Published online March 15, 2016. Reaction coordinates are of central importance for correct understanding of reaction dynamics in complex systems, but their counterintuitive nature made it a daunting challenge to identify them. Starting from an energetic view of a reaction process as stochastic energy flows biased towards preferred channels, which we deemed the reaction coordinates, we developed a rigorous scheme for decomposing energy changes of a system, both potential and kinetic, into pairwise components. The pairwise energy flows between different coordinates provide a concrete statistical mechanical language for depicting reaction mechanisms. Application of this scheme to the C7eq C7ax transition. The alanine dipeptide in vacuum revealed novel and intriguing mechanisms that eluded previous investigations of this well-studied prototype system for biomolecular conformational dynamics. Using a cost function developed from the energy decomposition components by proper averaging over the transition path ensemble, we were able to identify signatures of the reaction coordinates of this system without requiring any input from human intuition. Introduction. Many important biochemical processes, such as protein folding and enzymatic reactions, are rare activated processes that take place on a timescale orders of magnitude slower than that of elementary molecular motions. It is important, for both practical and purely theoretical purposes, to understand the underlying mechanisms of such activated processes in complex biomolecular systems on a rigorous ground. The prevalent picture for an activated process is a transition between two metastable basins on the free energy landscape separated by a barrier that is high compared to thermal energy. 1. The slow time scale arises from the fact that the system can rarely accumulate enough energy in the relevant degrees of freedom, DOFs, to surpass the transition barrier. This simple and elegant picture originates from reaction rate theories, such as the well-known transition state theory and Kramer's theory, 1-7, developed in the study of dynamics of chemical reactions of small molecules. A key concept in reaction rate theories is reaction coordinates. A few special coordinates that can fully determine the progress of a reaction process. 8-10. In particular, reaction coordinates must accurately locate the transition barrier. Otherwise, the resulting estimation of reaction rate will err significantly. For this reason, a quantitative and rigorous criterion for determining the correct reaction coordinates has been developed with the help of committer, PB8, 9, 11, 12. The probability that a dynamic trajectory initiated from a given configuration to reach the product basin before visiting the reactant basin. By this definition, the reactant and product states have committer values of 0 and 1, respectively, whereas the optimal transition state coincides with PB equals 0.5. Apparently, the committer provides a rigorous parameterization of a reaction process. Thus the intuitive, albeit qualitative, notion of reaction coordinates straightforwardly translates into a rigorous definition as the few coordinates that are sufficient for determining the committer value of any given configuration. Du et al. First adopted this rigorous definition of reaction coordinates in the context of protein folding. Chandler and co-workers established its usage as a standard practice in the general context of activated processes. 8. When this rigorous criterion is adopted, it turned out rather difficult to identify the correct reaction coordinates even for systems with modest complexity, using the traditional intuition-guided trial and error approach that enjoyed so much success in simple chemical reactions involving small molecules. One example is the C7eq C7ax isomerization reaction of the alanine dipeptide in vacuum. One of the simplest examples of biomolecular conformational transition. It was first found by Pairwise et al. 13 that the conventional Ramachandran torsional angles phi and psi, while sufficient for distinguishing the two stable basins, are inadequate for locating the transition state. Instead, another torsional angle θ1 was found to be an essential reaction coordinate. A rather counterintuitive finding. This counterintuitive nature of reaction coordinates turned out more often the norm than the exception in complex systems, posing an intimidating challenge to the intuition-driven approach. Indeed, the reaction coordinates of the C7eq alpha are isomerization of the same alanine dipeptide in explicit water solution already presented, a stumbling trial to our intuitions. 13,14. Motivated by this unexpected situation, more systematic approaches for identifying reaction coordinates were developed. The first of such methods was developed by Ma and Dinner, who utilized a combination of a genetic network and a neural network, GNN, to automatically choose from a pool of many candidates. The optimal combination of a pre-designated number of coordinates that predict the committer values for a database of pre-selected configurations with the highest accuracy. 15. They used this approach to identify the elusive reaction coordinate of the C7eq alpha R isomerization of the alanine dipeptide, which turned out to be a torque on the solute molecule derived from electrostatic forces from the solvents, reiterating the characteristic counterintuitive nature of critical reaction coordinates. The success of this machine learning-based approach encouraged development of other methods along the similar line, such as the method for maximizing the probability of being a reactive trajectory by Best and Hummer, 16. The maximum likelihood method by Peters and Trout, 17,18, and the kernel principal component analysis method by Antonio and Schwartz. 19,20. Although these machine learning-based automated methods enjoyed various successes, 15,18, 20, 21, two critical issues remain unsolved. One issue is that a machine learning method can succeed only if the candidate pool, from which it tries to select the correct reaction coordinates, contains all the reaction coordinates. Furthermore, if a machine learning method failed to find the correct reaction coordinates, one cannot learn any information about what variables were missing. The counterintuitive nature of reaction coordinates makes a candidate pool prepared by our intuition particularly prone to incompleteness. A more serious deficiency of a machine learning method is that it does not provide any additional mechanistic insight other than confirming our original intuition even when it does identify the correct reaction coordinates. This drawback holds equally true for the manual trial and error approach. For instance, we still do not have a clear mechanism on why theta-1 plays an essential role in the isomerization of the alanine dipeptide in vacuum, except for the intuitive but non-specific perception that it is likely to interact strongly with phi since the two coordinates share 3 atoms in common. In fact, a detailed mechanism that explains the dynamics of different DOFs by their mechanical interactions and relationships contains information more fundamental and valuable than reaction coordinates, and could serve as the foundation for identifying reaction coordinates. Reaction coordinates can be built from the detailed mechanism by proper averaging and filtering to extract information particularly important for determining the transition state and reaction rate. Knowledge of reaction coordinates without mechanistic understanding has more limited value. Therefore, it is desirable to have a method that can provide mechanistic understanding and derive reaction coordinates from such information. Aside from reaction coordinates, another concept closely related to reaction dynamics is energy flow. A classic topic in this area is vibrational energy redistribution, VER, 22,23, which provides the foundation for statistical treatment of reaction rate calculations. In small molecules, VER is often fast enough that equipartition is achieved before the reaction occurs. This is much less likely in complex molecules. In fact, based on normal mode analysis, it was found that the statistical characteristic of VER in proteins resembles that of VER in percolated polymers. 24. Another important topic is the dissipation of excessive heat of a system after it crossed the transition barrier or became excited by external energy input. Simulations suggested existence of preferred channels for heat dissipation in proteins. 25, 26. A very interesting suggestion is that promoting vibrations, 27, 28. Which are important reaction coordinates for some enzymatic reactions, are preferred channels of heat dissipation in lactate dehydrogenase. 29. However, to date there has been no study on energy flows during an activated transition process to our knowledge. A natural merge of the ideas of reaction coordinates and energy flow is that reaction coordinates are preferred channels of energy flow during an activated process, such that more energy flows into the reaction coordinates to help them cross the transition state barrier. Such an energetic view on reaction coordinates is appealing from a mechanistic standpoint. Potential and kinetic energies, or combinations of them, are the generating functions of the equation of motions in the optimal formulations of classical mechanics, be it Lagrangian or Hamiltonian. Since reaction mechanism has its root in the equation of motion, energy flow ought to be a proper language for describing the mechanism of a reaction process. Based on this idea, we developed a rigorous scheme of partitioning energy flows of the system among different degrees of freedom. More specifically, we considered the work on a given coordinate as the potential energy of the system that flows through it. In addition, we developed a rigorous procedure to decompose the work on a coordinate into a sum over pairwise components derived from its interactions with all the other coordinates in the system. We defined the so-called kinetic variable, vide infra, as a measure of kinetic energy associated with a given doof and a facility for gauging the flow of kinetic energy through each coordinate. We applied this scheme to analyze the detailed mechanism of the C7eq C7ax transition of the alanine dipeptide in vacuum, and uncovered a number of unexpected yet intriguing new features of this well-studied model process. Finally, based on the insights derived from the analysis of the reaction mechanism, we constructed a scoring function from work and kinetic variable of each coordinate that could potentially serve as a reliable signature of reaction coordinates, without requiring any input from human intuitions. 2. A procedure for decomposing energy and assigning energy flows. To obtain a mechanism of energy flow in a protein molecule, we first need to choose a coordinate system. For this purpose, internal coordinates, ICs, that consist of bond lengths, bond angles, and dihedral angles are more suitable than Cartesian coordinates. The latter does not properly account for the geometric constraints imposed on the dynamics of the system by the connectivity of the system due to chemical bonding, which are already incorporated into the definition of the former. A. Work as a measure of potential energy flow per coordinate. With an appropriate coordinate system at hand, the next step is to define the flow of potential energy associated with each coordinate. We need a proper definition of the change in the potential energy of the system associated with a given coordinate. The work Wi along a given coordinate Qi suits this requirement precisely. By definition, we have delta Wi of T1, T2, equals integral from Qi of T1 to Qi of T2 of Fi dQi equals minus integral from Qi of T1 to Qi T2 of partial of U of Q underscore vec on Qi dQi equals integral from Qi of T1 to Qi of T2 of partial of U of Q underscore vec on Qi dt equals minus integral from Qi of T1 to Chi T2 partial of U of Q underscore vec on Q underscore dot I dt. 1. Where Fi is the generalized force on Qi and U of Q underscore vec is the potential energy function of the system. According to this expression, Wi of T1, T2, is the change in the potential energy of the system derived from the motion of Qi along a stretch of trajectory between time T1 and T2 in the configuration space, under the hypothetical condition that all the other doofs of the system are frozen to their instantaneous positions on the trajectory during each differential step. Therefore, it is a projection of the change in the total potential energy during a segment of dynamic trajectory onto the motion of a specific coordinate, and can serve as a measure of the effects of the motion of the chosen coordinate gauged by the potential energy. As expected, work is a path-dependent quantity. In this way, the change in the total potential energy of the system during a stretch of dynamic trajectory can be decomposed into components along different coordinates. Delta U of T1, T2, equals U of T2 minus U of T1, equals minus summation over I of delta Wi of T1, T2, to where the summation is overall doofs of the system. B. Decomposition of work into energy flows from one coordinate to another. From a mechanistic point of view, understanding how potential energy flows from one coordinate to another is even more valuable than knowing how much energy flows through each coordinate. For this purpose, we are looking for a meaningful way to quantify how other coordinates contribute to the work along a specified coordinate through their interactions with it. The spirit from Sec. 2a can be utilized for this purpose as well. We only need to carry similar derivations to a higher order. Consider the evolution of the force on a given coordinate. Qi. Fi of t minus Fi of t1 equals minus Ui of t plus Ui of t1 equals minus summation over j of the integral from t1 to t of ui, j of tau, dqj of tau, equals minus summation over j of the integral from t1 to t of ui, j of tau, q underscore dot j of tau d tau, equals summation over j of delta fj to I of t1, t. ui equals partial of u of q underscore vec, on qi. ui, j equals second partial of uq underscore vec, on qi and qj. Delta fj to I of t1, t equals integral from t1 to t of ui, j of tau, q underscore dot j of tau d tau. 3 where ui, j denotes the change in the force acting on qi due to change in coordinate qj while keeping the other doofs of the system fixed. From this relation, we can obtain a decomposition of the work on qi. Delta wi of t1, t equals fi of t1, qi of t minus qi of t1, plus the integral from t1 to t of fi of tau, minus fi of t1, dqi of tau equals minus ui of t1, qi of t minus qi of t1, minus summation over j of the integral from t1 to t of dqi of tau cross the integral from t1 to t of ui, j of tau prime, dqj of tau prime equals minus ui of t1, qi of t minus qi of t1, plus summation over j of delta wj to I of t1, t. Delta wj to I of t1, t, equals integral from t1 to t of dqi of tau, integral from t1 to tau of ui, j of tau prime dqj of tau prime. 4 in accordance with the meaning of ui, j, delta w, I to I of t1, t, denotes the change in the system potential energy from time t1 to t, along a specific trajectory, derived from the change in the force in qi induced by the motion of qi itself. Under the hypothetical condition that all the other doofs are frozen to their instantaneous positions along the trajectory during each differential step, given this meaning, delta wi to I of t1, t, can be interpreted as the energy flow through qi projected onto the path charted by qi, weighted by the coupling of qi with itself. Alternatively, it can be viewed as an intrinsic potential energy profile that qi will experience along a given trajectory. By the same token, delta wj to I of t1, tj not equal to I, reflects the change in the system potential energy derived from the change in the force on qi induced by the motion of qj. Under the hypothetical condition that all the other doofs are fixed at their instantaneous positions along the trajectory during each differential step, accordingly, it can be viewed as the potential energy flow through qi projected onto the path charted by qj, weighted by the coupling between qi and qj. In this sense, it can be viewed as the flow of potential energy from qj to qi. In this expression, the term minus ui of t1, qi of t minus qi of t1, warrants special attention. It is a baseline term whose value depends on the choice of the reference point t1. It reflects the fact that we cannot decompose the force at time t1 without the knowledge of what happened before t1. Because the decomposition procedure is in fact a procedure for counting the accumulated impacts of the motions of different coordinates on the tagged coordinate qi. If t1 was chosen such that ui of t1 equals 0, then this term vanishes and we obtain a full decomposition of delta wi of t1, t. This fact can be used to develop a particularly convenient scheme for decomposing the work along a dynamic trajectory. At first, all the time points on a given trajectory with vanishing force, uit equals 0, are identified. Then the entire trajectory is divided into a sequence of segments. Each segment stretches between two time points where ui vanish. In this way, the work for each segment can be fully decomposed without any non-decomposable baseline term remaining. Also, all the force components are initialized to 0 at the first point of each segment of trajectory. The force components accumulated in the preceding segment will not be carried over to the decomposition of the current segment. We made this choice because the objective is to understand how the motions of different coordinates impact the motion of the tagged coordinate by changing the force acting on it. Therefore, only those motions that actually contributed to the force on the tagged coordinate should be counted. The force components accumulated during a segment exactly cancel out with each other at the end of the segment, and make no contribution to the force developed during the next segment. Therefore, they should not be artificially counted in the decomposition of the new segment. At this point, it is worth examining the results of this decomposition scheme on a potential energy function that can be straightforwardly decomposed into pairwise components in the conventional sense. We consider a potential function that only consists of additive pairwise interaction terms. U of r, vec equals summation over I less than j of u r I, j. As often encountered in simple liquid systems, the change in this potential energy function along a trajectory can be decomposed into pairwise terms in a straightforward manner. Minus delta UR vec equals minus UR vec T2 minus UR vec T1 equals summation over I of delta Wi of T1, T2 equals minus summation over I of the integral from T1 to T2 of partial U on RID, RIT equals minus summation over I. J where j not equal I of the integral from T1 to T2 of patrial U of Ri. J on RID Ri of T equals summation over I, j where j not equal I of delta Wj, I of T1, T2. Delta Wj, I of T1, T2, equals minus integral from T1 to T2 of partial U of Ri, j, on RID, Ri of T. 5. On the other hand, if we apply the scheme just developed, we obtain the following result. Minus delta UR vec equals summation over I, j of delta Wj to I of T1, T2. Delta Wj to I of T1, T2, equals minus integral from T1 to T2 dri of T integral from T1 to T of second partial of URI, j, on Ri, Rj drj of T prime, where j not equal I. Delta Wi to I of T1, T2, equals minus integral from T1 to T2 of dri of T integral from T1 to T of the summation f over j of second partial of U of Ri. J, on R squared I dri of T prime equals summation over j of delta Wi to I, j of T1, T2. Delta Wi to I, j T1, T2, equals minus integral from T1 to T2 dri of T integral from T1 to T of second partial U of Re, j, on R squared I dri of T prime. 6. Clearly, a delta Wj, I of T1, T2, term in the conventional decomposition scheme is a combination of delta Wj to I of T1, T2, and delta Wi to I to T1, T2 terms in the new scheme. Delta Wj, I of T1, T2, equals delta Wj to I to T1, T2, plus delta Wi to I, jT1, T2. The terms in the new scheme have more cleanly defined meanings as it allows a rigorous distinction between effects derived from self-coupling and cross-coupling. The decomposition procedure presented here is based on effects of the motion of different coordinates. Thus, it can further distinguish contributions from two interacting doofs that are considered equivalent in the conventional sense. See kinetic virial as a facility for measuring flow of kinetic energy per coordinate. The interconversion between potential and kinetic energies is an essential aspect of energy flow in a system, in analogy to work as the flow of potential energy. We also need a measure of the flow of kinetic energy through a given doof. This issue is particularly simple in Cartesian coordinates, as there is a rigorously defined kinetic energy content for a given doof x alpha. K to the power of Ca equals half p to the power of c, alpha x vec alpha equals half a meter alpha x vec squared, alpha. Where m alpha is the mass and p to the power of c, alpha is the linear momentum of x alpha. With k to the power of c, alpha at hand, the flow of kinetic energy through x alpha can be simply counted as change in its kinetic energy content. In generalized coordinates, Newton's equation is generalized to Lagrange's equation and linear momentum is generalized to the generalized momentum accordingly. Therefore, we can obtain a quantity analogous to k to the power of c, alpha. Ki equals half pi q vec I, as a measure of the kinetic energy associated with a generalized coordinate qi. By replacing the linear momentum with generalized momentum and the velocity of a Cartesian coordinate with the velocity of a generalized coordinate in the expression of k to the power of c, alpha, we refer to this quantity as the kinetic virial because of its similarity to the virial in its mathematical form. Given this definition, kinetic energy of a system can be decomposed as K equals summation over I of Ki. In this definition, Pi equals partial of E on slash Q vec I is the metric on how kinetic energy of the system will change with the velocity of Qi, playing a role analogous to that of force in the definition of work. In addition, the kinetic variable satisfies the equipartition relation. Bra Ki ket EQ equals half kBt, where T is temperature and bra middle ket EQ denotes equilibrium ensemble average. From this perspective, Ki serves as a good measure of kinetic energy per doof at equilibrium. In analogy to K to the power of C, alpha. Aside from these similarities between the kinetic variable and the kinetic energy per doof in Cartesian coordinates, they differ from each other with respect to their interconversions with potential energy. The equation of motion in Cartesian coordinates is P dot to the power of C, alpha equals minus partial U on x alpha, where the momentum of x alpha in Cartesian coordinates, P to the power of C, alpha equals m alpha x dot alpha, is a one-body quantity that only depends on x dot alpha. From this equation, we have delta W to the power of C, alpha equals minus partial U on x alpha delta x, alpha equals m alpha x dot alpha delta x alpha, equals delta, half a meter alpha x dot squared, alpha equals delta K to the power of C, alpha. 7 meaning that the work on x alpha completely converts into its kinetic energy. This fact suggests that delta W to the power of C, alpha and K to the power of C, alpha form a closed circuit, so that all the potential energy flowing through x alpha directly streams into its kinetic energy, and there is no leak to any other doofs. As a result, the kinetic energy changes in Cartesian coordinates do not contain any additional dynamic information that was not already embedded in the workflows. On the other hand, the equation of motion in generalized coordinates, the Lagrange equation, is P dot I equals partial L on Qi equals minus partial U on Qi plus partial K on Qi, 8, which differs from its counterpart in Cartesian coordinates in two aspects. First, Pi equals summation over J of a ij dot J is a many-body system-wide quantity, where Ai, J equals summation over alpha of m alpha to the power of P partial x alpha on slash Qi partial x alpha on slash Qj, is a function of the configuration of the system. As a result, the force on Qi affects velocities of all doofs in the system via its effect on P dot I. In addition, kinetic energy in generalized coordinates also depends on the configuration of the system due to the presence of structural factors, Ai, J, that couple velocities of different doofs together in a pairwise manner. As a consequence, we have delta Wi equals minus partial U on Qi delta Chi equals P dot I, partial K on Q underscore I, delta Qi equals P dot I delta Qi minus partial K on Qi delta Qi equals Q dot I delta Pi partial K on Qi delta Qi, not equal to delta Ki. 9 suggesting that potential energy flowing through Qi does not completely convert into its kinetic variable. Instead, a portion of the work converts into kinetic energy of the system in a broader manner and spreads into other doofs. Consequently, the interconversion between potential and kinetic energies carries extra dynamic information that is absent in workflows alone. And the structure of this interconversion process exhibits network-like features. If conversion of delta Y into delta Ki is still the main theme and leaks into other doofs can be considered more or less as perturbations, then kinetic variable still provides a good means for measuring kinetic energy flows in the network for potential kinetic energy interconversion. Such an approach leads to intriguing new insights into reaction mechanisms, as will be detailed in Sec. 3 and the supplementary material. 30. 3. Reaction mechanism of the C7eq C7ax isomerization of an alanine dipeptide in vacuum. To examine whether the energy decomposition scheme developed above is effective in uncovering reaction mechanisms, we applied it to the C7eq C7ax isomerization of the alanine dipeptide in vacuum. This system is a well-studied prototype of biomolecular conformational change and one of the smallest systems in which the non-reaction coordinates in the system can serve as a sufficient thermal bath to activate the reaction coordinates to cross the transition barrier. Bolyuis et al. First made the counterintuitive finding that the torsional angle θ1, figure 1, is an essential reaction coordinate, 13. In addition to the phi angle of the conventional Ramachandran dihedrals. Since then, the system has become a standard model for testing methods for identifying reaction coordinate. 15. However, the mechanical reason of why θ1 is essential for a transition that is fully defined by phi and psi has never been understood. Our objective is to clarify how the other coordinates participate in the transition of phi by analyzing how energy flows between different doofs of the system using the decomposition scheme developed in C7eq. Figure 1. A schematic representation of the alanine dipeptide molecule with the coordinates discussed in the main text. Alpha, angle 1C-2N-2C alpha. Beta, angle 2N-2C alpha minus 2C beta. Phi, 1C-2N-2C alpha minus 2C beta, θ1, 10-1C-2N-2C alpha, and psi, 2C beta minus 2C alpha minus 2C alpha minus 2C minus 3N. A proper average of work and work components to provide mechanism for barrier crossing. The reaction mechanism needs to be extracted from the ensemble of reactive trajectories, and we need to examine ensemble averaged quantities. For this purpose, we define the transition path ensemble average of a physical property as a function of a chosen parameter Zi of gamma, which is itself a function in phase space gamma equals qvec, pvec, as follows. Bra delta a z asterisk, ket equals integral d gamma rho of gamma, delta a of xi of gamma, to xi of gamma plus dxi, Dirac delta of xi of gamma, minus xi asterisk over slash integral of d gamma rho of gamma, Dirac delta of xi of gamma, minus xi asterisk. Bra delta a of xi asterisk, ket equals integral from z0 to xe asterisk dxe bra delta a of xe ket. 10 here, rho gamma d gamma is the probability of finding the system in an infinitesimal volume d gamma around the point. Gamma equals qvec, pvec, in phase space, delta. Delta, x, is the Dirac delta function. Delta a of xi of gamma, to xi of gamma, plus dxi, is the change in a along xi during the interval, xi gamma, plus dxi. And xi0 is the reference point for measuring delta a along xi. One useful choice of xi for mechanistic study is xi equals pb. Since the committer is the perfect parameterization of the critical transition period of a reaction process, to understand energy flows, proper choices for delta A are delta Wi and delta Wi to j. After examining bra delta Wi pb ket for all the 60 internal coordinates of the system, we found that only delta W phi, pb, and delta W theta 1 pb are non-vanishing in the interval of pb element of 0, 1, figures 2 and S130. This fact demonstrates that on average only the motion of phi and θ1 during the critical transition period consistently invokes appreciable changes in the potential energy of the system. In accord with the fact that they are the most essential reaction coordinates of this process. However, this information does not disclose how phi and θ1 interact with each other, and how they interact with the rest of the system. For this purpose, we examined delta Wi to phi of pb and delta Wi to θ1 of pb, with qi being another doof of the system. Figure 2. Averaged work, bra delta Wx pb ket, and kinetic virial, bra delta kx pb ket, as functions of the committer for different coordinates. Black, delta W phi, pb. Red, delta W theta 1 pb. Blue, delta W phi, pb, plus delta W theta 1 of pb. And the dashed lines are the corresponding kinetic virials. B. The master-slave relations among a small set of tightly coupled coordinates. In this process, we found that there are only 3 other coordinates. The other Ramachandran torsional angle psi and 2 bond angles alpha and beta, figure 1. That interact with phi and θ1 significantly. Together, these 5 coordinates form a closed clique of interacting doofs, within which there is a significant flow of potential energy on average during the critical transition period. In the following, we will focus on energy flows among these coordinates only. Figure 3 shows the flow of potential energy between each of phi, theta 1, psi, alpha, beta, and the rest of the set. The energy flows between beta and the other 4 coordinates are almost identical to those of alpha. One can change alpha to beta in the indices in figure 3 and obtain the corresponding diagram for beta, dashed lines in the lower right panel of figure 3, revealing an almost perfect symmetry between alpha and beta, which is consistent with their nearly symmetric relationship with respect to phi. A close inspection of the energy flow terms in figure 3 reveals a number of intriguing features. First, all the other coordinates share higher energy flows with phi than with each other, making phi the obvious principal hub for energy flow and reiterating its central importance for the transition process. Second, with the exception of theta 1, the self-coupling induced work flows, i.e., the broad delta Wi to IPB terms for all coordinates, are negative and high in magnitude. Thus, the observed motion of each of these coordinates faces high intrinsic barrier and is highly disfavored if the other coordinates were frozen. On the other hand, the cross-coupling induced work flows between phi and the other doofs are large and positive, meaning the observed motion of phi facilitates the observed motions of the other doofs and vice versa, reflecting a strong synergy among the coordinates involved. This is an intuitive and appealing picture. But the mechanistically more important question is whether this energy flow structure reflects causal relationships among the coordinates involved, whether the observed motion of phi drove the observed motion of the other doofs or the other way around. Or, alternatively, relationships between these coordinates could also be mutually symmetric. They are synergistic on an equal footing and no causality is involved. The answer to this question is closely related to a long-standing idea in the field of protein dynamics: the concept of fast coordinates being slaved to slow coordinates. 31 to 33. In this context, the reaction coordinates are the slow or master coordinates, whereas the faster coordinates are the slave coordinates. One prominent example in this line of thoughts is the notion that the dynamics of protein molecules are slaved to the slow modes of solvent dynamics, such as the modes related to the alpha relaxations. On the other hand, if the time scales of the coordinates involved are similar, no slaving or causal relationship exists, and their interdependence is symmetric. While this concept is intuitively appealing, so far a definitive and reliable signature for slaving is still lacking. A close inspection into the relation between delta Wi to phi, Pb, where Qi equals alpha, beta, and delta W phi to IPB suggested some intriguing clues to this question. Among the 3 coordinates involved, alpha and beta are bond angles, which are considered the stiff or fast coordinates, whereas phi is a dihedral, which is considered a soft or slow low-frequency coordinate, a notion that underlies the earlier attempts to simulate the dynamics of dihedral angles alone to capture the essence of protein dynamics. Indeed, closer inspection into the detailed dynamics of alpha, beta, and phi revealed that both alpha and beta will open up to reduce the barrier faced by phi as it crosses the transition barrier, figure S230, as if they were pushed by phi to open up. An effect resembling what one would expect in the classical example of the rotation around the carbon-carbon bond in ethene. This observation motivated us to propose that delta Wi to JPB greater than delta Wj to IPB, if the motion of Chi is faster than that of Qj and Qi, is slaved to Qj. Figure 3. Averaged work components. Delta Wi to JPB, as functions of the committer for different coordinates. Black, x equals phi. Red, x equals theta 1. Green, x equals Ci. Blue, x equals alpha. And magenta, x equals beta. The dashed lines in the lower right panel are delta Wx to beta Pb. Next we observe that delta W psi to phi, Pb, greater than delta W phi to psi, Pb, suggesting psi is faster than phi based on our hypothesis. Since psi is not a critical reaction coordinate based on what we learned from previous studies, 13,15, presumably its timescale is faster than that of phi, consistent with the conclusion derived from our hypothesis. With regard to the relation between phi and theta 1, we found delta W phi to theta 1 of Pb greater than delta W theta 1 to phi of Pb. suggesting theta1 is much slower than phi. A conclusion in accord with the fact that theta1 is an essential, albeit counterintuitive, reaction coordinate. In fact, in rare cases where a reactive trajectory happens to contain a failed attempt of phi to cross the barrier before it tried again and succeeded, the motion of theta1 actually induced a huge prohibitive force on phi and bounced it backward. Concurring with the notion that phi has to wait for theta1 to move into the right position to allow phi to move forward and pass the barrier. Figure S3 to the power of 30. In addition, the momenta of phi and theta1 are closely correlated around the transition period, with the change in p theta1 slightly preceding the similar change in p phi, figure S4 to the power of 30, conveying a sense that the motion of phi follows the motion of theta1 or phi is slaved to theta1. Similarly, the velocities of phi and theta1 are anti-correlated, with phi showing slightly more oscillations than theta1. Figure S5 to the power of 30, suggesting the timescale of phi is faster than that of theta1. Finally, we also found that delta W alpha to beta of Pb approximates delta W beta to alpha of Pb, suggesting that the timescales of alpha and beta are very similar, consistent with their identity and their symmetric relationship with phi and with each other. By similar arguments, we can conclude that theta1 is slower than psi, and both alpha and beta are faster than psi and theta1. Consistent with the conclusions we drew above, this fact suggests that the conclusions derived from the hypothesis proposed here are self-consistent, a necessary condition that needs to be satisfied for the hypothesis to be correct. Altogether, the conclusions we can derive from this hypothesis are both self-consistent and fully consistent with what we have learned about this reaction from previous studies, a fact that corroborates this hypothesis. In fact, the relation between slaving and the asymmetry in the relevant work components can be understood quite intuitively, between a pair of master and slave coordinates. The motion of the slave coordinate is more adaptable because of its faster timescale. Therefore it has to adjust its own course to yield to the master coordinate, so that changes in the force on the master coordinate induced by the slave coordinate movements will be along the direction of and appear to facilitate motions of the master coordinate. Consequently, its contribution to the work on the master coordinate accumulates constructively and consistently, leading to a large magnitude. On the other hand, the motion of the master coordinate is not constrained by the slave coordinate and does not necessarily facilitate the motion of the latter. Consequently, its contribution to the work on the slave coordinate varies more stochastically and does not accumulate in a consistently constructive manner, leading to more cancellations. Since the coupling strength between the two coordinates is symmetric, the work component that accumulates less constructively will have a smaller magnitude, leading to the observed asymmetry between the relevant work components associated with the master and the slave coordinates. In addition, a number of features in the energy flow diagrams readily concur with our intuition on this process. The first observation is that the intrinsic barrier along phi, delta W phi to phi of Pb, plateaus at Pb equals 0.5. Consistent with the expectation that only the process of climbing up the barrier consumes energy and the barrier top coincides with Pb equals 0.5. In contrast, the intrinsic barriers along the other coordinates do not share such close correlation with the committer, and mainly reflect the ruggedness of the energy landscape they experience, concurring with the expectation that their impact on the transition process is mediated through their interactions with phi. The coupling between theta1 and phi is tight only up to the point of Pb equals 0.5, reflected by the fact that delta W phi to theta1 of Pb plateaus at that point. This feature is consistent with our intuitive picture that the critical period of a transition process is during climbing up the barrier, and an essential reaction coordinate would participate mainly in that process. The same correlation with the committer is also observed in the couplings between phi and alpha, beta. On the other hand, the coupling between phi and psi remains strong even after the point Pb equals 0.5. Consistent with fact that both of them are involved in specifying the stable basins. Although these observations do not provide as decisive insights as does the distinction between slow and fast coordinates, it is nevertheless reassuring to have well-defined mechanical quantities with direct link to dynamics that can scrutinize and verify our intuitions, as well as elaborating on them explicitly. C. Kinetic energy associated with theta 1 is used to assist barrier crossing of phi. In Cartesian coordinates, the force acting on a coordinate x alpha affects x dot alpha only. Thus the work on x alpha completely converts into kinetic energy of x alpha. In contrast, in generalized coordinates, the force acting on a coordinate qi can affect velocities of all the coordinates in the system. This feature provides an interesting mechanism through which a portion of the energy added into qi in the form of work, delta wi greater than 0, can be transferred to another coordinate through the mediation of kinetic energy. Although this type of energy transfer should be of secondary significance and smaller magnitude compared to work, it is a distinctive mechanism of energy flow and could play a critical role in a transition process. Given the subtlety of reaction dynamics, to understand energy transfer mediated by kinetic energy, we first examine the overall structure of kinetic energy of a system and its conversion with potential energy. The pairwise additive and quadratic form of kinetic energy, K equals half summation over I of a 2q dot I squared, plus summation over I, j where ji of a iq dot iq dot j, lends itself to a simple schematic picture. We can view kinetic energy of a system as a compartmentalized pool, figure 4. Each compartment corresponds to a specific term in K. Thus there are nn plus 1/2 kinetic energy compartments, KECs, in a system. The amount of energy stored in a compartment, I, j, is a iq dot iq dot j, or half a 2q dot I squared if I equals j. Energy cannot flow directly between different KECs, but they can flow into and out of potential energy channels, PECs, due to the interconversion between potential and kinetic energies, figure 4. A PEC I, corresponds to the work, delta Wi, along a coordinate qi. Thus there are n PECs in the system, and the amount of energy that flows through PEC I is delta Wi. Each PEC can exchange energy with all the KECs in the system, but is likely to exchange significant amount of energy with only a few of them. Figure 4. Upper. A schematic diagram showing that PEC I transfers significant amount of energy to PEC J at 3 KECs. The endpoints of an arrow indicate the relevant PEC and KEC that exchange energy with each other, and the direction of the arrow indicates the direction of energy flow between them. Lower. A schematic diagram of the energy flows among alpha, beta, psi, theta 1, and phi as a summary of results discussed in the text. Arrow denotes a positive energy flow from the starting coordinate to the end coordinate. Blocked arrow, vertical bar, denotes a negative energy flow from the starting coordinate to the end coordinate. Red color denotes a large magnitude. Black color denotes a small magnitude. Solid lines denote work, and dashed lines denote energy transfer, mediated by kinetic energy via the direct mechanism. Apparently, the combined PEC-KEC system has a complex network structure in general. Energy can flow between different components of this network via direct or indirect mechanisms, driven by the interconversion between potential and kinetic energies. A direct mechanism refers to a one-step process in which PEC I pours energy into, whereas PEC J extracts energy out of the same KEC. Energy transfers directly from PEC I into PEC J via this KEC, figure 4. An indirect mechanism means that energy transfer between two components went through multiple steps of intermediate PECs and KECs. Understanding indirect mechanisms requires fully understanding the overall network structure, which is generally a daunting challenge. A direct mechanism, due to its simplicity, could be identified and understood in a pairwise and one-to-one manner. Thus we focus our discussion on the direct mechanism only, as demonstrated in the supplementary material, 30. A PEC usually has significant energy exchanges with more than one KEC. Thus, two PECs can directly exchange energy with each other at multiple KECs. It is important to determine the total amount of energy exchanged between two PECs in order to decide the actual directionality and magnitude of the overall net energy transfer, as detailed in the supplementary material, 30. Delta Wi minus delta Ki provides a convenient means for bookkeeping the total amount of energy transfer conducted by PEC I, and can produce clear signatures when the mechanism of transfer is sufficiently simple. Among the different scenarios of energy transfer via the direct mechanism, the simplest case is that PEC I delta Wi greater than 0 transfers significant amount of energy into only one PEC J. Delta Wj less than 0 And pec J receives energy only from pec I as well. This scenario is also the easiest to appreciate in the context of reaction dynamics, as it clearly identifies an energy donor and an energy acceptor. The donor facilitates the motion of the acceptor by donating energy to it, as detailed in the supplementary material, 30. This case has a particularly simple and clear signature that requires simultaneous satisfaction of the following conditions. Bra delta Wi ket greater than 0, delta Wj less than 0, bra delta Wi ket vertical bar and delta Wj are significant. Bra delta Wi ket minus bra delta Ki ket greater than 0, delta W. J minus delta Kj less than 0 semicolon vertical bar, bra delta Wi ket minus bra delta Ki ket vertical bar and delta Wj minus delta Kj are significant. Bra delta Wi ket plus delta Wj approximates bra delta Ki ket plus delta Kj. 11. A close inspection into the results in Figure 2 revealed that the works and kinetic virials of θ1 and phi satisfy this set of conditions remarkably well. Thus we are tempted to infer that a significant portion of the energy collected by θ1 from the other parts of the system is utilized by phi via the kinetic energy-mediated direct transfer mechanism to facilitate crossing the barrier on phi. This observation further underpins the essential role of θ1 in the transition process of phi. To briefly summarize, the mechanism of the C7eq C7ax isomerization consists of the following essential points. Lower panel of Fig.4. Only 4 coordinates, alpha, beta, psi, and θ1, interact strongly with the major transition coordinate phi, whereas the rest of the system serves as the thermal bath in the standard sense. 34 to 36. Among them, alpha, beta, and psi stands in the way of phi transition, causing a high intrinsic barrier that phi needs to cross. But they are slaved to phi and yield to its movement to reduce its barrier. On the other hand, phi is slaved to θ1, so that θ1 actively drives phi across its barrier. In addition, the energy collected by θ1 is also used by phi for barrier crossing through the mediation of kinetic energy. D metrics that can serve as signatures for identifying reaction coordinates. Given the effectiveness of work and kinetic virial in mapping out and elaborating the underlying mechanism of a reaction process, it is natural to expect that they should be useful in developing metrics for identifying reaction coordinates. A logical expectation is that work and kinetic virial projected onto reaction coordinates should show a clear and regular structure compared to those projected onto non-reaction coordinates. Results from projecting work and kinetic virial onto the committer, Figure 2, corroborate this reasoning. Since the committer is a perfect statistical reaction coordinate, even though it provides no insights into reaction dynamics, we define a projection of a quantity A onto a coordinate xe as bra delta az asterisk ket s equals integral d gamma rho gamma delta a off xi gamma to xi gamma plus delta xi Dirac delta of xi of gamma minus xi asterisk si dot of gamma over slash integral of d gamma rho of gamma Dirac delta of xi of gamma minus xi asterisk s of xe dot of gamma equals 1 if psi dot gamma greater than 0, minus 1 if xi dot gamma less than 0. 12 where the meanings of different terms are the same as those in EQ. 10 and delta xi is the bin size along xi. The only difference between bra delta az asterisk ket s and bra delta az asterisk ket is the presence of the dynamic directionality factor sxe dot gamma in the former. As a result, if the system passes through a bin in the backward direction, xi dot gamma less than 0, its contribution to bra delta az asterisk ket s for that bin will cancel with the contribution from a pass in the forward direction. Xi dot gamma greater than 0. Therefore, if a coordinate undergoes frequent oscillatory motions, as one would expect for a non-reaction coordinate, the final average will likely cancel out and be very small. By contrast, the motion of reaction coordinates should be more directional and coherent, leading to less cancellation and more prominent signatures. We note that both work and kinetic virial along the essential reaction coordinates show clear and significant changes during the transition period, and they contain complementary information of the reaction mechanism. To emphasize the features of both, we defined a scoring function. Delta Li equals delta Wi plus delta Ki as the quantity to be projected onto coordinate Qi. In this way, the features in work and kinetic virial will reinforce each other, enhancing the chance that a clear signature of reaction coordinates can emerge from the projection. With this scoring function, we found that only phi and theta1 show significant and regular features in projections, figure 5. Whereas these quantities for the other coordinates are essentially zero within sampling errors. Although the current system is rather simple and has been solved by trial and error approaches, either manual or informatics-based and automated, this is the first time that a signature of reaction coordinate directly derives from straightforward ensemble average of quantities bearing mechanistic significance without input from human intuition. Figure 5. The scoring function for identifying reaction coordinates. Left, phi, and right, theta1. The scoring functions are computed according to EQ, 12, and scaled by the bin sizes to remove dependence on bin size. 4. Concluding remarks. In this paper, we proposed a framework of viewing an activated reaction process as stochastic energy flow biased towards preferred channels, which we deemed the reaction coordinates. To materialize this energetic view of reaction processes, we developed a scheme for projecting the changes in potential and kinetic energies of the system on top motions of different degrees of freedom. In particular, we developed a rigorous procedure for projecting the work on a given coordinate, which we identified as the flow of potential energy through the tagged coordinate, onto the motions of itself and other coordinates interacting with it. We further defined kinetic virial as the means to measure the flow of kinetic energy associated with a given coordinate. This scheme for decomposing changes in energy allows us to map out the mechanism of a reaction process as a network of energy flows between different DOFs. To examine the effectiveness of this approach, we applied it to a standard model system for conformational changes in protein molecules, the C7eq C7ax transition of the alanine dipeptide in vacuum. This system was the subject of a few previous investigations, and its reaction coordinates have been well documented. Thus it can serve as a good test case of the new approach. To our delight, with the help of a single assumption that the asymmetry between the work flows between two coupled coordinates reflects the difference in the characteristic timescales of their respective dynamics, we were able to derive the detailed mechanism of this reaction that is both self-consistent and fully consistent with what was previously known about the reaction. In addition, a few intriguing new facets of the reaction mechanism were revealed by the new approach. Furthermore, with a proper procedure for averaging over the reactive trajectory ensemble, the essential reaction coordinates naturally emerge as the only coordinates that carry significant flows of potential and kinetic energies, which is consistent with our hypothesis that they are the preferred channels of energy flows, without requiring any intuition-based input. This is a distinctive advantage in comparison with the previously developed informatics-based approaches. Although this example is known to have an energetic bottleneck, we expect the method to be applicable to processes with entropic bottlenecks. For such processes, we expect that the kinetic virial component of bra delta Li ket will provide the distinctive signature for reaction coordinates. In addition, we expect that this approach can also be applied to study energy transduction processes, such as Vara and heat dissipation, and yield valuable new insights. On the other hand, this energy-oriented standpoint is only developed to a very primitive stage. Extensive and systematic studies are required to examine its effectiveness and consolidate its foundation. One subject of importance is our hypothesis on the relationship between the work components and the timescales of the relevant coordinates, which remains a conjecture at the current stage. Extensive studies of model as well as real systems will be required to scrutinize it and flesh out the details. Another issue is to reduce computational cost, as the committer evaluation is expensive. In this regard, we expect that procedures along the line of EQ 12 can be used to avoid the committer in the projection of work components. Also, the approach needs to be extended to incorporate generalized coordinates other than internal coordinates. Of particular interest is to apply it to study solvent dynamics, which are believed to be dominating protein dynamics in many important situations, and are notoriously difficult to deal with due to the indistinguishability of solvent molecules. Our scheme allows us to decompose the energy change into a combination of one-body and pairwise terms, but this decomposition is achieved through usage of partial derivatives. Thus, the resulting one-body and pairwise terms are conditional. With the conditions specified by the definitions of partial derivatives, these conditions need to be properly taken into account in a coherent and consistent manner when we elaborate on physical implications of the conditional quantities. This requires extensive testing on a large number and diversity of models as well as real systems. Methods. All simulations were performed using the molecular dynamics software, Suite GROMACS 4.0.737, with transition path sampling implemented. 38,39 Amber 94 force field was used to facilitate comparison with previous results. 40 to 42. The structure of the alanine dipeptide was minimized using steepest descent algorithm and heated to 300 K using velocity, rescaling with a coupling constant of 0.2 ps. 43. The system was then equilibrated for 200 ps and no constraints were applied. The time step of integration was 1 fs. Basin C7eq was defined as -200 less than phi -55 and -90 less than psi less than 190. Basin C7ax was defined as 50 less than phi less than 100 and -80 less than psi less than 0. Transition path sampling was used to harvest 6,000 independent reactive trajectories from C7eq to C7ax. Transition paths were 2 ps in length and simulated with a constant energy of 36 kilojoules per mole, which was chosen to ensure an average temperature of 300 K for the transition path ensemble. Alternatively, sampling of the canonical ensemble with constant energy trajectories can be achieved using the algorithm developed by Giesler and Chandler. 44. All the averaged quantities discussed in the text were averaged over 6,000 trajectories. The committer for each configuration was estimated with 1,000 shooting trajectories. Each trajectory with a maximal duration of 2 ps. For larger systems, computational cost for evaluating committers could be significantly reduced with a fitting procedure we recently developed. 45. In the computation of energy flow quantities, exact separation between internal and external DOFs was achieved by proper choice of external coordinates, as detailed in a recent publication. 46. Acknowledgements. Funding support from the National Institutes of Health. No, RO1GM086536 is acknowledged. We thank Dr. Stuman for help with figure preparations. We also wish to thank the anonymous reviewers for their thoughtful comments and suggestions that helped to improve the manuscript greatly. W. Lai and A. Ma. J. Chem, Phys. 144, 114103, 2016 1D. Chandler, Statistical Mechanics of Isomerization Dynamics in Liquids and Transition State Approximation, J. Chem, Phys. 68-6, 2959 to 2970, 1978. 2H. A. Kramers, Brownian motion in a field Offershund theta diffusion model of chemical reactions, Physica 7-4, 284 to 304, 1940, 3p. Petukas, Statistical Approximations in Collision Theory, in Dynamics of Molecular Collisions Part B, edited by W. H. Miller, Plenum, New York, 1976, p. 269. 4e. Wigner, The Transition State Method, Trans. Faraday Soak. 34, 29 to 41, 1938. 5p. Hange, P. Tochner, and M. Borkovec, Reaction Rate Theory, 50 years after Kramers, Reverend Maud Phys. 62-2, 251 to 341, 1990. 6b. J. Byrne, M. Borkovec, and J. E. Straub, Classical and Modern Methods in Reaction Rate Theory, J. Phys. 9213, 3711 to 3725, 1988. 7e. Policon P. Tochner, Reaction Rate Theory. What it was, Where is it today, and where is it going? Chaos 15-2, 026116, 2005. 8p. G. Boluise, D. Chandler, C. Delago, and P. L. Geisler, Transition Path Sampling, Throwing Ropes Over Rough Mountain Passes in the Dark, Ann. Reverend Phys. Chem. 53, 291 to 318, 2002. 9r. Du et al., on the transition coordinate for protein folding, J-Chem Phys. 108-1, 334 to 350, 1998, 10 watts. J. Lee and A. Ma. Recent developments in methods for identifying reaction coordinates, mol, simul. 4010 to 11, 784 to 793, 2014, 11d. Writer. On the eigenfunctions of the Fokker-Planck operator and of its adjoint, Physica A 142 1-3, 103 to 121, 1987. 12 liters. Onsager. Initial recombination of ions, Phys. Rev. 54-8, 554 to 557, 1938. 13p. G. Boluise, C. Delago, and Chandler, Reaction Coordinates off Biomolecular Isomerization, Proc. National, ACAD, Sci. USA 9711, 5877 to 5882, 2000. 14t. A. McCormick and D. Chandler, Grid Flux Method for Learning the Solvent Contribution to the Mechanisms of Reactions, J. Phys. Chem. B. 10712, 2796 to 2801, 2003. 15a. Ma and A.R. Dinner, Automatic Method for Identifying Reaction Coordinates in Complex Systems, J. Phys. Chem. B. 10914, 6769 to 6779, 2005. 16r. B. Best and G. Hummer, Reaction Coordinates and Rates from Transition Paths, Proc. National, ACAD, Sci. USA 10219, 6732 to 6737, 2005. 17b. Peters, G. T. Beckham, and B. L. Trout, Extensions to the Likelihood Maximization Approach for Finding Reaction Coordinates, J-Chem Phys. 127-3, 034109, 2007. 18b. Peters and B. L. Trout, Obtaining Reaction Coordinates by Likelihood Maximization, J-Chem Phys. 125-5, 054108, 2006. 19d. Antonio and S. D. Schwartz, The Stochastic Separatrix and the Reaction Coordinate for Complex Systems, J-Chem Phys. 13015, 151103, 2009. 20d. Antonio and S. D. Schwartz, Toward Identification of the Reaction Coordinate Directly from the Transition State Ensemble Using the Kernel PCA Method, J. Phys. Chem. B. 11510, 2465 to 2469, 2011. 21j. Hu, A. Ma, and A. R. Dinner, A two-step nucleotide flipping mechanism enables kinetic discrimination of DNA lesions by AGT, Proc. National, ACAD, Sci. USA 10512, 4615 to 4620, 2008. 22m. Gruebel and P. G. Woolens, Vibrational Energy Flow and Chemical Reactions, H. E. Chem, Res. 37-4, 261 to 267, 2004. 23s. A. Rice, An Overview of the Dynamics of Intramolecular Transfer of Vibrational Energy, Adverb Chem Phys. 47, 117 to 200, 1981. 24d. M. Leitner, Energy Flow in Proteins, ANU. Reverend Phys. Chem. 59, 233 to 259, 2008. 25 volts. Botan et al. Energy Transport in Peptide Helices, Proc. National, ACAD, Sci. USA 10431, 12749 to 12754, 2007. 26h. Fujisaki and J. E. Straub, Vibrational Energy Relaxation in Proteins, Proc. National, ACAD, Sci. USA 10219, 6726 to 6731, 2005. 27d. Antonio and S. D. Schwartz, Internal Enzyme Motions as a Source of Catalytic Activity, Rate-Promoting Vibrations and Hydrogen Tunneling, J. Phys. Chem. B. 10523, 5553 to 5558, 2001. 28s. L. Keetman and S. D. Schwartz, Reaction Coordinate of an Enzymatic Reaction Revealed by Transition Path Sampling, Proc. National, ACAD, Sci. USA 10430, 12253 to 12258, 2007. 29A. Davorifer, D. Antoniou, and S. D. Schwartz. The promoting vibration in human heart lactate dehydrogenase is a preferred vibrational channel, J. Phys. Chem. B. 11551, 15439 to 15444, 2011. 30C supplementary material at http://dx.doi.org/10.1063.1.49435881 for detailed discussion of energy transfer, mediated by kinetic energy and figures S1 S6, 31p. W. Fenimore, H. Frauenfelder, B. H. McMahon, and E.F.G. Perrick. Slaving. Solvent fluctuations dominate protein dynamics and functions, Proc. National ACAD, Sci. USA 9925, 16047 to 16051, 2002. 32p. W. Fenimore et al., bulk solvent and hydration shell fluctuations, similar to alpha and beta fluctuations in glasses, control protein motions and functions, Proc. National, ACAD, Sci. USA 100-140, 14408 to 14413, 2004. 33 volts. Lubchenco P. G. Woolens, and H. Frauenfelder, Mosaic Energy Landscapes of Liquids and the Control of Protein Conformational Dynamics by Glass-Forming Solvents, J. Phys. Chem. B. 10915, 7488 to 7499, 2005. 34e. Cortez, B. J. West, and K. Lindenberg. On the Generalized Langevin Equation, Classical and Quantum Mechanical, 826, 2708 to 2717, 1985. 35r. Swansik, Nonlinear Generalized Langevin Equations, jstat.phys.93, 215 to 220, 1973. 36r. Swansik, Non-Equilibrium Statistical Mechanics, Oxford University Press, Oxford, 2001, p. 37b. Hess et al., Gromax 4, Algorithms for Highly Efficient, Load-Balanced, and Scalable Molecular Simulation, jchem.theorycompute.43, 435 to 447, 2008. 38f. Grader and W. Lee, Transition Path Sampling with Quantum/Classical Mechanics for Reaction Rates, Methods Mol, Biol, 1215, 27 to 45, 2015. 39 watts. Leont, Greater Atomistic Evidence of How Force Dynamically Regulates Thiol/Disulfide Exchange, J.M. Chem. Soc. 13247, 16790, 2010, 40d. A. Kcet al. Amber 5.0 University of California, San Francisco, 1997. 41a. J. DePaul et al. Equilibrium Conformational Dynamics in an RNA tetraloop from Massively Parallel Molecular Dynamics, Nucleic Acids Res. 3814, 4856, to 4867, 22, e. J. Soren and V. S. Ponda, Exploring the Helix Coil Transition via All-Atom Equilibrium Ensemble Simulations, Biophys. J. 884, 2472 to 2493, 2005. 43g. Bussy, D. Donadio, and M. Parinello, Canonical Sampling through Velocity Rescaling, J. Chem. Phys. 126-1, 014101, 2007. 44p. L. Geislerand, Chandler, Important Sampling and Theory of Non-Equilibrium Salvation Dynamics in Water, J. Chem. Phys. 11321, 9759 to 9765, 2000. 45 watts. J. Lee and A. Ma. Reducing the Cost of Evaluating the Committer by a F-ITting Procedure, J. Chem. Phys. 143, 174103, 2015. 46 watts. J. Lee and A. Ma. Some Studies on Generalized Coordinate Sets for Polyatomic Molecules, J. Chem. Phys. 143, 224103, 2015.